Here we go with part 2 of the 5.2 lesson. Just when things seem to be getting easier, we have to mix it up. In this case, I'm going to give you arc length, and I'm going to ask you for radius. Don't panic. Go to the formula and start filling in what you know. I know arc length, 58.25. I don't know the circumference, but I know the formula, pi times diameter over 1. And I do know what portion of the circle. Now in this case, the copy didn't come through well. We're after this arc. That central angle is 40. So the portion of our circle is 40 over 360. Now I really don't like to deal with 40 over 360. When I cancel my zeros, 4 over 36, I know that I'm really talking about 1/9 of my circle. Basic algebra problem at this point, dividing by 9. So I'm going to multiply both sides by 9. And that is going to give me an answer I can't find in my notes. 524.25 equals pi d. Pi is being multiplied times the diameter, so I'm going to divide both sides by pi. This is a case where you'll want to use the pi key on your calculator and actually divide this out. So I'll find out that the diameter is equal to 166.9. How do I get from diameter to radius, which I want? Divide by 2, and my radius is 83.4. It's best if you wait until the very end to round your answers, which is why my rounding is off just slightly. Now we just have some theorems that I want to run through. They all feel very good common sense-wise when you think about them. The arc-chord congruency theorem says in the same circle or in congruent circles, two minor arcs are congruent if and only if their corresponding chords are congruent. Remember again, if you know congruent arcs, you get congruent chords, or if you know congruent chords, you get congruent arcs. If this piece and this piece are equal, no matter how I slide them across my circle, it should feel good that the part they cut off, that arc they cut off, is the same. And that's all that theorem is saying. So using that theorem, this first example, if my arcs are congruent, my chords are congruent. And that sets us up with a very simple algebra problem of 7x minus 2 equals 5x plus 6. Subtract 5x, add 2, and x is 4. Now the perpendicular bisector theorem, this is a theorem we have seen before with triangles. I talk about it as the guide wire problem. A diameter or radius of a circle is perpendicular to a chord if and only if, remember that works both ways, it bisects the chord and its arc. So these arcs are also equal. If you're wondering where the guide wires are, they're right here. And when we learned about this in terms of triangle, we learned that these guys were also equal, which makes perfect sense because those are radii of the circle. And so is this. So all three of those red pieces are equal. Now that's kind of a trick with triangles. Always look for diameters or radii, and if they're not drawn for you, go ahead and draw them in, because in this case there's no direct way to find the length of OC, but you could find the length of OA, because as soon as I draw that in with that perpendicular bisector, I have a right triangle. And that is a common picture and a common problem. Congruent chords theorem is pretty similar to the one right before this, but basically if I'm equidistant from the center, that whatever chord is created at that point is congruent. So in the same circle, in congruent circles, two chords are congruent if and only if they're equidistant from the center. So if you know equidistant from the center, you get congruent chords. If you know congruent chords, you get equidistant from the center. And again, I see the ability to draw triangles in and create some problems there that could become proofs later on, just to plant a seed. Parallel chords theorem. If two parallel lines are the same distance apart for all of infinity, because that's what they are, it should make perfect sense that the arcs they create would be equal. Now, a couple of examples, and given circle Q, WX is 10 and WPR is 150. So this is 10, and this arc right here is 150. Now the theorem that we had, that perpendicular bisector theorem, says that not only is this segment bisected, but this arc is bisected. So that makes WP 75 degrees, because bisect means to cut in half. That makes WR 20, because XR is 10. Now C is where things start to get interesting. If Q to X is 5, find QP. And as I just said, there's no direct way to find QP, but QP is the same as QW. And as soon as I draw that in, I have a triangle that looks something like this that can be solved with the Pythagorean theorem. R squared would be equal to 5 squared plus 10 squared. And remember, the hypotenuse is always opposite the right angle. And so I'm looking at R squared being equal to 25 plus 100. R squared is equal to the square root of 125. So R is approximately 11.2. Given circle Q and SR equal to TU, prove that those arcs are congruent. And we're not going to go through a formal proof. We're just going to reference the theorem that proves this, and that is the arc chord theorem. But just in preview, notice that all four of these segments would be equal because they're radii, and I see a couple of triangles that are congruent by side, side, side. Our last example is that given that MQ, the measure of MQ is equal to the measure of NP, find X. Well, the chords or the arcs are congruent from the given, so it's a matter of setting up a simple equation, adding 27 to both sides, dividing by 2. Now, if you would like a little challenge problem, number 4 is a challenge problem, you need to remember SOHCAHTOA. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. Ignore the numbers, pay attention to the coordinates. D to F is this arc right here, and the hint is that it is related to this right triangle right here, which has an x coordinate of 5 and a y coordinate of 12. And so by the Pythagorean theorem, and actually don't even need the Pythagorean theorem, but you could find the radius, just 13. You can find this angle by using your trig ratios. If you remember, I am talking here about the opposite and the adjacent, because this arc is related to this central angle. And so opposite over adjacent, I'm looking at the tangent of the angle I don't know, and I'm just going to call it alpha, it's a trig thing, is equal to 12 over 5. Alpha is like the variable. We undo the tangent ratio by using that inverse key on your calculator. And you'll find out that it's 67.4 degrees. Make sure your calculator is in degrees. You can work through and give those a try. These are arc measure. These are arc length. What you'll find here, EF is a similar triangle right there with a smaller angle. Once you have A and B done, C and D are a matter of using the arc length formula. If you want to come see me about those and see if you did